Hello and welcome to my computational presentation about OLEDs and protein stretching. Now part 1 of this lab aimed at identifying the use of the molecules, in this case the cut version of TME-PA and cut TM-PYPB, for use in the hole transport layer and electron transport layer of an OLED device. To do this, the energies of a series of states was calculated using Orca in NanoHub, and the orbitals of the HOMO and LUMO orbitals of each molecule were then plotted in VMD. So the necessary information to find the energies for the ground state, triplet state, the singlet state and triplet state, the cationic and anionic state, were provided in the form of XYZ files, canvas, and to plot the orbitals in VMD, we provided with cube files for each molecule. As you can see here, on Orca in NanoHub, this is the input, and highlighted in yellow is where it input the spin and charge. This shows a singlet state, the TME-PA molecule, where the spin obviously is 1 for singlet and charge would be 0. If it was a triplet state, the spin would be 3, charge 0. Cationic, the spin would be 2, with a charge of +1. For anionic, the spin would also be 2, with a charge of -1. And this would yield different energies. As seen here, the energies of cut TME-PA are as follows. The energy of a triplet state is -543,898 kilocalories per mole, and I'm not going to read them all out. As you can see here, the most negative value is singlet state, which in this case is the ground state. This is more stable. Now the ionization energy and electron affinity were calculated from the cationic and anionic states respectively by taking the cationic state and subtracting the ground state, in this case the singlet state, from its energy to find the difference. And same was done for the ionization, the electron affinity, excuse me. Here is the HOMO and LUMO plotted in VMD of the cut TME-PA. On the right hand corner, there is the LUMO with an energy of a -0.0645 electron volts. And on the bottom left is the HOMO with an energy of -4.6219 electron volts. Now for a cut version of TM-PYPB, the energies are as follow. Yet again, the singlet state is the most negative state, and as such is the ground state. And the ionization energies and electron affinities were again calculated through the cationic and anionic states respectively. As you can see, if you subtract -445212 from -445387, you end up with 175 kilocalories per mole. Up right again, the LUMO of the cut TM-PYPB has an energy of -0.9674 electron volts, and the HOMO has an energy of -6.1065 electron volts. Now, what do the HOMO and LUMO of both molecules tell us is their suitability for hole transport layer material and electron transport layer material. Now, the LUMO of the cut TME-PA molecule is very close to 0 at -0.0647 electron volts, and is also a slightly higher in energy than the LUMO of the cut TM-PYPB. This sort of would indicate that the material would be more suitable for hole transport layer, as it would prevent the transport of electrons and allow for the hole transport layer to the emission layer in the OLED device. Now, additional information which sort of helps confirm that the PA molecule is suitable for HTL material and the PB molecule is suitable for ETL material, electron transport layer material, is that the HOMO of the TM-PYPB is far lower and far more negative than the HOMO of the PA. And as a result, having a more negative HOMO or lower HOMO means that it would be able to transport electrons more effectively to the emission layer. Now for the second part of the lab, we use a stretch molar nanohub and stretch proteins under 3 different parameters. As you can see here, on the left is the temperature, which uses constant, which is 300. The number of steps in this case is for 10,000, but we change this between 10,000 in the x-axis and z-axis, as well as 5,000 in the x-axis. So 3 different parameters. As you can see here, parameter 1 is the protein before and after. The bottom left is before, top right is after. After the protein was stretched in the 5,000 parameter in the x-axis, you can see the water molecules are going with the protein in this case. In parameter 2, these are the before and after images of the 10,000 protein stretching in the x-axis, and even more stretching, as you can see, than the 5,000, which obviously makes sense. And the water molecules are further spread out yet again. And finally, parameter 3 is stretching of 10,000 in the z-axis. Now, obviously, in each case, the water molecules, or some water molecules, remain associated with the protein structure. And obviously, this is likely due to the hydrogen bonding between the protein structure and the water, as certain parts of the protein would be polar, or just lead to some intermolecular interactions with the water and the protein.